Thanks for joining us for this random repair. Now what we have here is a power supply board for a Samsung Syncmaster 2220 WM computer monitor. Now what this board is having issues with is that when it was installed in the monitor would try and power itself on, but for some reason it wasn't reaching the proper voltage in order to activate the backlight, and the monitor would end up turning itself off, and then the light at the bottom of the monitor, which is blue, would start flashing. Now this indicates that the power supply board is not providing enough voltage and current for those circuits to operate properly. So I broke into the monitor, pulled out the power supply board, and gave it a once over, and as you can see, all of these capacitors over here have markings on the top. Every single one of those capacitors are bloated. So if we just take a brief look at the top, you can see how the top of the capacitors are a little raised. That tells me that those capacitors have gone bad. These are your basic electrolytic THT capacitors, and this will commonly happen. So I've done a little research on these power supply boards, and I've noticed that this is a common issue with the Syncmasters. So today what we're going to do is I bought some new capacitors. They're all Nichicon capacitors. They're really reputable manufacturer. They produce high quality components, and I'm going to take those and I'm going to install them into this board. But they're not exactly the exact same value as these capacitors that are here. So what I've done is I decided to experiment a little bit. So I wanted to see if the issue with these capacitors consistently failing was caused by either a runtime issue for the hours that the component is rated to run for, or if it's a fact that the components are meeting the minimum threshold that is acceptable for the device to function. So I have increased the voltage value of these capacitors by approximately 25 to 50%, and in some cases even upwards to 100%, just to see if that will help mitigate some of these issues later on down the road and help us achieve a longer longevity of this device's ability to function inside of the monitor and to make sure that it's actually stable. So if you're curious about the numbers that are printed on the board so you can make sure that this board is similar to the one that you may be working on, these are going to be the numbers that are printed at the top of the power supply circuit board, so you can go ahead and pause your screen to jot those down. And then also at the very bottom we have this sticker right here with the reversion number for the board. Looks like it's going to be a revision A, so go ahead and also pause your screen. I'll try and get you a little closer in so that sticker is a little more easily identifiable there. Okay. Now I did want to mention that the one thing I love about these Samsung boards that are produced for Samsung or just a large name brand manufacturer is that they have a lot of data that's printed on the board. So you have the pictures of components where certain areas would be populated. You also have this list right here that gives you the pinout for this connector on the side of the board, which is fan-friggin-tastic. And then also as we rotate the board over to the back, you have this second number printed up here on the backhand side. You also have this sticker right there. Let's see if you can get a closer look at that. There you go. And as you noted, there are many different notations on the backhand side of this board. And the reason why I like this feature being on the board is because you can identify the components on the backhand side without having to constantly flip the board back and forth to try and figure out what components you're working with. Now you notice a few little hash marks, see right there and right there. That is going to be helping me identify what connections that I'm going to want to load up with solder to try and desolder some of these components. But on those connections you can tell that here there is the universal symbol for a capacitor, and then all the hash marks where you can see that is going to be the same. And then also a great thing is we'll see if we can try and get you a little closer in here. I apologize for it wiggling around. You see that plus sign right there? That's designating where your anode and your cathode belongs on the board for your electrolytic caps. Now, I also love this feature because not only do you not have to specifically remember the orientation that you're pulling the capacitor out, and just in case you forget the orientation of where your anode and your cathode is supposed to go inside the circuit, you can always look at the backhand side to figure out which one is for which hole because of this notation. So not every board is going to have this. The larger manufacturers do this to try and help their assembly personnel in the factory populate the board properly so everything is in its proper orientation before they go through the solder flow process. Sometimes you're not even going to have any inkling whatsoever about how a component is supposed to go inside of the circuit board, other than remembering or taking a picture of how the component was oriented before you remove it. So what I recommend doing is, before you start pulling any component out of a board, either jot down, make some notes, draw yourself a diagram, heck, even take a picture of it and write some notes on the picture itself, so you can designate where your components are supposed to go, where the anode and the cathode is supposed to go inside the circuit, and that way you won't put in something backwards and possibly fry something else in the circuit that you really don't want to mess up. So what we're going to do is we're going to go ahead and grab our preheated soldering iron, and personally, when I'm removing stuff, I like to use a angled blade tip like this. And I also like to flow some new solder into the joint, introduce some fresh solder to help the thermal transfer from the soldering iron tip to the board, so it makes it a little easier to try and remove the components without burning up your traces or marring up your board. Another thing that I like to use is going to be this Kester 186 no clean flux. I use Kester all the time for a lot of my work. It seems to be a great brand of flux. It helps the solder flow very well. You don't get a lot of oxidation in your joints get wetted thoroughly, and you get a really good mount for your joint to the PCB surface for the traces and the connection. So what I'll do is I'll go ahead and flow some new solder in some of these joints, then we'll start taking some of these components out. Now that we added some solder onto each of these joints, there's a couple ways that you can actually remove the components from the board. Some are going to be technically correct, some are going to be little shortcuts that's going to make this job a little easier. So the technically correct way is to grab some solder wick and go through here and soak up all of the solder from each joint so that the components are loose, the through hole connection is broken, and that you can just remove the component from the board. Now, the easier way, and what I like to do, as long as you're careful and you try and keep a eye on how much heat you're putting onto the joints, making sure you don't, one, burn yourself, and two, overheat the component, is using a larger tip soldering iron, a larger tip on your soldering iron like this, to where you can actually heat up both of your joints simultaneously, and using your other hand on the backhand side of the board, just completely pull out whatever component that you are trying to remove. And what that does is it just makes it a little easier so you can get the component out, and then later on, if you really want to clean up some of that old solder, you can go through with some desoldering braid, soak up all of that old solder so you have some nice clean pads to work with. So what I'm going to do is I'm going to go ahead and use that technique where I use a single soldering iron tip, heat up both joints, and just completely pull the component through the holes and off of the board. Now this first one I'll do as a demonstration just so you know exactly what I'm talking about. So I'm going to take the board, I'm going to tip it up on its side like so. Try and get this area right here into view. And then I'll take my soldering iron. I'm going to heat up both connections at the same time while pulling the component through. As you can see, the legs are no longer inside of the THT connection. And here's your component right there. So I'm going to go ahead and do that with all of my components and then swap them out individually. You can either pull them all simultaneously and just repopulate them after you get all of the old ones pulled out. What I like to do personally is to make sure that I don't forget to populate an area, is I'll work one part at a time. So now I've populated some of those new capacitors into their resting place in the circuit, and what I've done is I fed the legs of the capacitors through and I bent them over like you can see there. That holds your component in place so you don't actually have to hold it while you're soldering it in. I like doing it this way just because, one, I can get the components as close as possible to the board, and two, it frees up my other hand so I can use to feed in my solder here at the same time that I'm applying heat to the joint. At this point, I will go ahead and throw a little more flux on there just to make sure that the joint wets properly and that I get a good solid connection. I can go back in after the joint cools, grab my flush cuts here and snip off each individual leg. Now, I like to save these legs of the capacitors because they make great jumpers if you're doing a small or a somewhat larger trace repair on some PCB board that was damaged and you have to go in and you need some type of jumper material. I like to use Kynar wire. I also like to use some coated motor winding wire in order to try and bridge a connection or something similar to that effect. But these are just convenient because what you can do is you can tack them in and then you can take it to the other side of the trace that you're wanting to repair, or you can also use them as jumpers. So if you need a jumper on any part of the board, for example, this board actually does have jumpers on it, as you can see right there, and those legs are perfect for replacing those. So I'll go ahead and flow some new flux on the joints, flow some new solder into the joints and get those cut, and we'll work on our way to the other capacitors on this side that need to be replaced. So now that those four capacitors in place, I went ahead and snipped off the legs that were protruding through, and I like to personally go back over and re-wet the joint just to make sure that I get a properly wetted and secured joint, and so I can get those nice peaks on the solder joint that you're looking for. So basically what you want to see is you want to see your solder joints have like a little peak like that. If they are a round bubble around the joint, that means you have too much solder in there. If you don't have a peak and it seems a little flat, that means you don't have enough solder in your joint. So just make adjustments as you go through. As you become more experienced with soldering, you start to pick up on learning how your joint should properly look. They should be shiny instead of dull like this is up here. That means that your joints were properly wetted and that it is not a cold joint. So a cold joint is where the solder does not properly bond the component to the board and that there is a weakness in that joint, and over time that solder joint can break, causing intermittent connection issues with your circuitry. So as a circuit board heats up and cools, it expands and contracts. That cycle over a period of time can break your solder joints because of the expanding and contracting, and it'll fracture around the circumference of the component, or it'll fracture closer towards the board. And basically, as soon as it gets hot, it'll normally function properly, but as soon as it cools down and that board contracts, it opens up the gap in the broken solder joint, and then you get a circuit that's not behaving properly. So we're going to go ahead and go through these three components here, take those out, replace them with other components, and we'll take a look at some of the other components on the board to see if we're going to want to try and replace them. Even though they're not showing any signs of failure, doesn't necessarily mean that they shouldn't be replaced as a preventative measure. So we're going to go ahead and replace those, and we'll take a look at the other capacitors on this board. So now I've replaced these two capacitors over here. I'm going to turn the board around, and this is what I was talking about when you want to try and make sure that you get components that are going to be compatible with what you're using. So what I did is I replaced this 10 volt 1000 microfarad capacitor with a 35 volt 1000 microfarad capacitor. So I increased the voltage rating on the capacitor, which should help improve longevity of the circuit and reliability. But because of the size profile difference, you can see that they're pretty much stacked up right next to one another. With the older capacitors, there was a little more wiggle room in between the two, and these barely fit in there together. So that's going to be something you want to watch out for if you're going to be improving upon or replacing components in a circuit, and you have to be conscious of the component footprint. So all of these other electrolytics throughout the circuit actually look fine, and I haven't noticed any issues with them. However, since these components down here that are the workhorse of the circuit through here failed, there's a high likelihood that the age of these smaller components could affect performance. Now, I don't know what their tolerances are currently. I have not actually pulled them from the circuit to measure if they're within acceptable ranges of operation in terms of the capacitance. But what I would like to do is to see if I have any capacitors that are compatible with those sections of the circuit, and see if I can also replace those. So I was able to find some compatible electrolytic capacitors on hand. So let's just take a look at what we replaced. This is a 47 microfarad 25 volt electrolytic, and what I used to replace it is going to be a 47 microfarad 100 volt electrolytic capacitor. So when you're replacing electrolytics, you can always go higher on the voltage rating for your replacement caps. You want to stay within 10% of your microfarad rating. If you get any further off than that, you could run the risk of having some unintended consequences with your circuitry. But the voltage increase isn't going to hurt anything, because that is the maximum voltage threshold at which that capacitor is rated for. So in theory, shouldn't have any issues in this circuitry whatsoever. Now, we do have a few more capacitors throughout this circuit that I want to try and see if I can find replacements for, and it's going to be, here, let's get you into frame here. It's going to be these four right here. So it looks like I just happen to be in luck. I actually have on hand some 220 microfarad 25 volt capacitors, and I'm going to use those to repopulate those areas. And there you had it. That is every single electrolytic capacitor replaced on this board, with an exception of this guy right here. So this is going to be the main capacitor. Sorry for bumping the camera there. It's going to be 150 microfarad at 450 volts. Now that's going to be a capacitor that I'm going to have to do some research on. A lot of times, especially in, we'll use arcade cabinets, for example. The power supplies in the old arcade cabinets has these large capacitors, and they tend to go bad after about 30 or some odd years, possibly into 40 years. But the thing is that these capacitors are going to be the main capacitor for the circuitry for the high voltage side. Now, it is always a good idea to replace these after a certain period of time. I'm going to have to look up and see when the Samsung Syncmaster 2220 WM that I have, that this board goes to. I'm going to have to look up the year of production and see when this board was actually produced, and maybe consider replacing that. But for right now, we're well within the usable time frame of this device that we shouldn't need to replace it for quite a while. So thank you for tuning in for the first episode of a random repair. I'm the kind of person that likes to tear apart a device that quits working or that isn't working properly, trying to troubleshoot the device to figure out why it's not working and see if I can improve upon the original design or repair the device so that it's usable again. So if you did enjoy the video, please click that like button down below. Also, don't forget, Rehab Gaming channel has numerous videos on there to kind of guide you through the process of different repairs, troubleshooting, some ideas, basic troubleshooting skills, solder rework, and stuff like that. So if you're interested in those types of topics, please check out the other content available on our channel. So without further ado, thank you for stopping by, and we hope you have a wonderful day.